In the previous session, we have solved a problem which was the ready mix problem using simplex method. What we identified there that the constraints were written in the smaller than equal to type. So in that case, we were adding the slack variable and we were solving the problem. As and when we are adding a slack variable, our starting basic feasible solution was the static basic feasible solution is always the origin, where the variables of the problem are taken as non-basic and the slack variables we consider as a basic at the beginning. But the problem arises when our model has greater than type or equality constraints. It is because whenever these type of constraints are there, then our LP will become ill-behaved. Ill-behaved in a sense that the static basic feasible solution which we have taken earlier, that was origin, that will become infeasible for the such kind of a problem. In this case, what we do is we can use artificial variables so that they can play the role of slack at the first iteration, and then we are going to dispose them legitimately at the later iteration. There are two methods to deal with such kind of LP model which have either greater than type, equal to type, or both of them type. These methods are called as M method and two-phase method. Let us begin with an example here. We want to minimize a function z, and we have first equality constraint, second is greater than type, third is smaller than type, and we have x1, x2 greater than 0. Let us convert them into the equation form. Since it is already equality constraint, so we are not adding any slack variable or surplus variable. For equation number 2, we are subtracting a surplus variable, which is now represented as x3. For equation number 3, we have a slack variable added. Now from this particular format, as we know that our starting basic feasible solution, say origin. Origin means if I put x1 and x2 equals to 0, then what will be the value of x3? Now let us look at equation 1. Now x1 is 0, x2 is 0, means 0 equals to 3. So it is ill-behaved. Now if I put in the second equation x1, x2 equals to 0, then x3 is equals to -6, which is infeasible. So what we can see here is as and when we have equality or greater than type, our static basic feasible solution, which was 0 and a 0, that is the origin, we cannot take it. The other points. Now the question is, can I take other point? Yes, we can take any other point, but that point should make sure that our starting solution should be feasible, means the basic solution should be feasible. Now, since it is a two variable problem, we can think of some value of x1 and x2. But if it is a large variable problem, we cannot. And therefore, in order to devise, we are using the M method in this, and then we will also discuss the two-phase method. Now, as we have understood that this particular equation form is ill-behaved. So what we are going to do here is we will be adding artificial variable. So first artificial variable will be for the first equation because it is equality constraint. And the second artificial variable will become for the second equation because it is greater than type. So we are going to use two artificial variable R1 and R2 in this formulation. So let us see that. So here we have added artificial variable R1 and R2. Now here This method says that as long as we are including these artificial variables, then we have to penalize our objective function. Since it is a minimization problem, we are adding a penalty in terms of m into r1 plus m into r2. M is a very large constant value and r1 and r2 are our artificial variable. Now looking at this particular equations, now we have 6 variables. X1 and X2 are problem variables. X3 and X4 are surplus slack variables. R1 and R2 are artificial variables. And we have 3 equations. So we can see that number of basic variable is 3 and number of non-basic variable 6 minus 3 will become 3. So 3 basic, 3 non-basic variables in this particular problem. So here the objective function z we are going to write in our equation form. So we are taking the right hand side onto the left hand side. So I have written an equation equals to the right hand side is 0. Now question is how we can choose the basic variable because we have to start. Now as we remember that let me take equation number 1. The additional variable is r1. So I will be taking r1 as my basic variable. Then let me take equation 2. In this case, I have surplus variable and artificial variable. So the thumb rule is whenever there is an artificial variable, we should take it first. So that's why in equation number 2, we have taken r2 as our basic variable. Now in equation number 3, it is very straightforward because it is a slack variable. So we have taken x4 as our basic variable. So r1, r2 and x4 are our basic solution variables and rest of the variables are non-basic variable. The question is what should be the value of m? As I said, m should be large value because if I'm adding m r1 plus m r2, basically I'm penalizing the value of a z. Since I want to minimize it, I'm adding a very large value. So this m value for a current example, we have taken 100. So what is the penalty here? The meaning of penalty is that if R1 and R2 has some positive value, the value of a Z is high. So I'm penalizing it. But when R1 and R2 value will become 0, then the Z will become 4x1 plus x2. And that is the role of penalization. So let us start with the very first iteration in which the simplex table is written here. Now, as we remember that the columns are corresponding to the number of variables. So we have written as x1, x2, x3, r1, r2, x4. And we remember that the last column is corresponding to the right hand side. Now here we started with the Z row followed by the first basic variable from equation 1, equation 2 R2 and equation 3 X4. As per our previous discussion on simplex method, we are going to write the coefficients. So X1 coefficient is -4, then -1, minus m. So that's why we have written -4, -1, 0, because there is no coefficient of x3 in objective function. Then m is taken as 100, so -100, -100, 0, and the right hand side is 0. Similarly, if I look at the equation number 1, that is constraint 1, coefficient is 3, 1, and R1 is also 1. So 3, 1, coefficient of x3 is 0, coefficient of R1 is 1, 0, 0, and the right hand side is 3. So we have written under the column of solution. Similarly, I can fill all the entries for R2 row and X4 row. Now currently, we know that X1 and X2 are basic variable. Currently, X1 and X2 are non-basic variables. So their value is 0. So R1 will become 3. Similarly, X1 and X2 are 0. and x3 is also non-basic. So R2 value is 6. Now, if I take these R1 and R2 value putting into our Z, so we know that it is not going to be 0, meaning that our 0 is inconsistent. So how we are going to handle this inconsistency? We will be performing some row operations. So row operations means that we will be making the coefficient under R1 and R2 0. How we can make it? I multiply 100 with R1 row, add into the Z row. Similarly, I multiplied 100 into the R2 row and added into the Z row. So this is the formula which we have given. So 100, how we got the 100 value? Based on the coefficient written under R1 and R2. Once we do it, this is the simplex table which we will get it. So the coefficient of R1, R2, R3 rows will remain the same, only Z will change. Now we remember that the problem which we are solving is the minimization problem. So the optimality condition, or how to find the entering variable, it depends on the most positive value. So the entering variable will be most positive value corresponding to x1. So this is what we have identified as the entering variable. Now, then we can find the ratio. So we are going to divide 3 divided by 3, 6 divided by 4, 4 divided by 1. So I get the ratio, and the leaving variable will be corresponding to the minimum non-negative ratio, which is R1. So we find R1 is going to leave. So I get by pivot row corresponding to the entering variable, pivot column corresponding to the entering variable, pivot row corresponding to the leaving variable. Once we do, we have to apply the Gauss-Jordan row operation. Since these operations we did it in the last session, I'm showing you the table directly. Now, in this case, the table is given. So before I go further, let me show you that if you look at the basic variable R1, R2, and X4. So if you look at the coefficient, these are again coefficient of identity matrix. So this we are preserving here. Now I'm coming to this particular table. After applying Gauss-Jordan row operations, we get this table. Now the entering variables, so the most positive coefficient in Z row is 167. Once we find the entering variable, now we have to find the leaving variable. We are going to calculate the ratio. The minimum ratio is corresponding to R2. So we have identified pivot column corresponding to X2, pivot row corresponding to R2. Then again, we have to apply the Gauss-Jordan row operation. Now this particular, since we did it, so I am showing you the result directly. Here, once we reach here, then we have to again see, is there an entering variable? So we know yes, X3 can enter because it has the most positive coefficient in Z row. Similarly, I can find the ratio, and then we will get to know that X4 is going to leave it. Once we have identified pivot column and a pivot row, we will be applying the Gauss-Jordan row operations. Now this is the table which we get it. Now look at the coefficient of a Z. And if I'm looking for the non-basic variable, which as per this iteration, X1, X2, X3 are basics. So R1, R2, and X4 are non-basic. None of the coefficient in Z row is positive. So this means that there is no entering variable. As per our simplex method, since there is no entering variable, so we should stop it. So when we are stopping our iteration, the optimum solution is, now again read this, Z, and looking at the solution column. So the value of a Z is 17 by 5. Value of X1 is 2 by 5. Value of X2 is 9 by 5. Value of X3 is 1. And that is the optimal solution for the given problem. Now let us discuss two-phase method. Now in M method, we have to use M penalty. Now here in the previous case, we have taken m as 100. Now what is the problem here is that some objective function which are complex and written in terms of large number of a variable. If we take a value of m less, then m method is not going to give us a good result. And so that's why choosing the value of m is a little sensitive to the problem. And there is always a possibility of round of error, and that may impair the accuracy of the simplex method calculation. This can only happen when the m value is equivalent to the objective function value. So in order to remove this user defined value m, we have another method called two-phase method. How it works? In phase one, we attempt to find the starting basic feasible solution for the given problem. Second, we invoke phase two is invoked to solve the original problem. So we remember that whenever we are starting a simplex method, we always start from the origin. In the m method also, when we have taken x1, x2 as our non-basic variable at the beginning, this means that we were starting at the origin. Now we know that the origin is infeasible solution. So in phase two, again, we will be starting with the origin, but we will first find the basic feasible solution. And from that basic feasible solution, we are going to solve the original problem. Let us see how. So this is the problem which we have solved in the previous example. We are going to take the same and going to solve the same problem using two-phase method. Now phase one. Now these equations, since we know that for constraint one, we will be adding artificial variable. For constraint two, subtract one slack surplus variable and then artificial variable, and constraint three, a slack variable. And we are going to have a 6 number of variables. So in this case, these constraint equations are familiar because we have done it in the previous example and number of variable. Look at the objective function. Now the objective function is written as minimize R. Now we are not writing Z, we are writing R as R1 plus R2. How we decide this? So basically, any artificial variable in the problem, we are going to take the summation of all artificial variable in the problem and we want to minimize. Now you know that any variable that is artificial variable or other variable, they should be non-negative. So what could be the minimum value of R, small r? It should be 0. It can only be 0 when R1 is 0, R2 is 0. This means R1 and R2 is 0 means they are going to be non-basic. Non-basic has no role in the optimization in the objective function. So our objective is we are in the phase one, we are going to minimize a small r, which is the summation of all artificial variables. And then slowly and slowly, let us remove these artificial variables from the simplex table. Let us see how. So this is the simplex table. We already discussed how R1, R2 and X4 can become our starting basic feasible solution. Now here we have a row corresponding to R rather than Z. Now we have X1, X2, X3, R1, R2 and R4. These columns we are familiar with. Look at the coefficient of R. Now in the phase one, since we are minimizing this, no coefficient of X1, X2, X3. Coefficient of R1 is -1. Why -1? You remember that we take this R1 and R2 on the left hand side so that the right hand side is equal to 0. So here my R1 is -1, R2 is -1, coefficient X4 is 0, and the solution is 0. These are the coefficients that are the same as we have discussed in the previous example when solving the same problem using M method. Now here, as we understood that X1 and X2 are going to be non-basic, so R1 is basic the value of R1 is 3. Similarly, value of R2 is 6. Now, if I'm going to put in the objective function, this will become 9. But the current problem says that the solution of the value of a small r is 0, which is inconsistent. How we can do it? We can perform the row operations as we did it in the last example. So we are going to make the coefficient of artificial variable 0. So how we can do it? I can take R1 row and add it into the small r row. Similarly, I will take R2 row and then I will add it into the small r row. This is what I have written at the bottom. If I do so, I can get the change in the coefficient of r row, and rest of the coefficient will remain the same. It is a minimization problem. So what is the most positive coefficient? X1. So this is going to enter. Then I can find a ratio, and based on that, I can say R1 is going to leave. So it is pivot row. So this exercise I'm leaving to you, that you do hand calculation. Make sure that you can get R1 as a pivot row by finding the ratio. So one particular column will be added at the end. Once it is done, then we have to apply the Gauss-Jordan row operation. If we do so, I can get the simplex table as we can see here. So the change in the coefficient are written here. Again, what is the most positive coefficient? X2. Based on that, I can find the ratio, which variable is going to leave. R2 is going to leave. Then we again perform the Gauss-Jordan operation and we get the table at the bottom. Now here, what you will see that it is a minimization problem and there is no coefficient which is positive for the non-basic variable, meaning that if there is no entering variable, we should stop it. And we will stop, and this is the optimal solution for the phase 1. Look at the solution. Now X1 and X2 and X4 are basic solution and corresponding values are given. Is this solution feasible? Yes. Why? Because X1 is greater than 0, X2 is greater than 0, X4 is also greater than 0, and the other variable R1, R2 and X3, they are already non-basic, means they are 0. So we can say that this could be the static basic feasible solution for the problem. So this is the end of phase 1. Now what we will do in phase 2? So since, as I have discussed, there is no entering variable, this is the optimum solution for phase 1. So what we are going to do in phase 2? We are going to eliminate columns of the artificial variable. If I go back, so this R1 and R2, these two columns, we can delete it. If I delete, I can get a short table here, a smaller table as compared to the previous one. First change. Second change is, look, we have removed the Z row, we have removed the R row. Now we are including the Z row. Now Z row is corresponding to our original objective function. So you know that the left hand side you are taking on the, you know that this right hand side you are taking on the left hand side, and the right hand side will become 0. So -4, -1, 0, 0, and it is 0. Now the question is why we are removing the artificial variable, and we did not remove these artificial variable with M method. Why we are removing with the two-phase method? We are removing these two R1 and R2 only because when we perform the computation, you know that we have to change the coefficient of R1 and R2. Since R1 and R2 are already non-basic, means they are already 0, they are not going to play in our objective function. Now you can see there is no R1 and R2 in the original function. So in order to reduce the number of computation, we have reduced R1 and R2. But in M method, we have preserved the value, we have preserved these two columns. So the computation in M method will be more as compared to the two-phase method. So in order to save some computation, we have removed R1 and R2. Now, as you can see, the value of a Z is inconsistent. Why? Look at the value of X1. X1 is 3 by 5. X2 is 6 by 5. if I put into my objective function, it is not going to be 0. It is a value. So what we can do here is we know that we have to do 4x1 plus x2. So we will be making the coefficient of x1 and x2 0. Why? Because these are the basic solutions. And as we are following that, since it is inconsistent and x1, x2 variables are given in our objective function, let us make their coefficient 0. So the operations which we are going to done is 4 times of x1 row plus 1 times of x2 row. This one we are going to add it. So we get the table like this. Now there is a one observation. We know that under the basic variable, the coefficients are always identity matrix. Now look at this x1. X1 is basic. So the coefficient, if you look at this, this is identity matrix coefficient. Similarly, x2, similarly, x4. Now you can observe that what are the coefficient of x1, x2, x3, basically the basic variable under Z. You will see that the basic variable, the value of a Z is always 0. So under x1 is 0, x2 is 0, and x4 is 0. So I'm giving this exercise to you. You look back the first simplex method which we have solved it in the previous session. You look the M method. In all of the cases, the coefficient of Z, coefficient under Z row, the coefficient of basic variable under Z row are always 0. So that you just see, and that is 0. Why? Because you remember that x1 has entered, and then that's why x1 is here. And as soon as it will become 0, as soon as it will become basic, the coefficient will become 0 because it is not going to enter or it is not going to leave the table here. With this understanding, let us go ahead. So since it is a minimization problem, we will be looking for the most positive value of the non-basic variable, which is currently x3. So x3 is going to enter. And when we find the ratio, we will see that x4 is going to leave. Now I'm leaving this exercise to you that you will be needing one more iteration here so that you will get the final solution as x1 is equals to 2 by 5, x2 is equals to 9 by 5, and the value of a z is 1755. So you do one more iteration of simplex method and you will get the solution. So with this, I'm concluding this session 2 on simplex method. In this session, we mainly focused on the problem which have equality constraint or greater than type of constraint or both of them together.